In the last little bit of the unit, we've been looking at how adding energy or removing energy from a substance can have it change phase. We've looked at how the temperature affected the phase of something. But temperature is not the only thing that matters. Pressure is as well. Now, we talked about pressure a little bit before, but let's look at what happens if I put a substance in a container. If this was just water and we left it in an open container for several days, we would probably expect that over time the water level drops. And that's because water is made up of little molecules that are in constant motion, and they are exchanging energy with their environment. And so occasionally some of these particles are going to collide and grab some energy, and they will evaporate and float out. But if I close this container, then that evaporated particle hits that and bounces around. And that particle bouncing off of the container wall, that causes pressure. Pressure is really force over area. You guys are familiar with the American unit of pressure, I suppose, PSI, pounds per square inch. The SI unit is in Pascal. This is a Newton per square meter. This is a Pascal. That is not very much pressure. It's like if you took a quarter pound of weight and spread it out over a meter square section of floor. And so we actually use kilopascals, 1,000 pascals, kPa, usually when we're dealing with pressure. And so the atmosphere exerts about 14.7 pounds per square inch on a surface. So that's the atmospheric pressure in PSI. That's about 100 kPa. So even a kilopascal is quite a bit smaller than a PSI, pound per square inch. Anyways, there's a couple ways we can make gas pressure go up. I can put more particles in a container, right? When you blow up a balloon, the pressure in there goes up because you're adding more gas to it. And so they hit the walls because there's more of them. They hit the walls more often. Because they hit the walls more often, the pressure's going up. The other thing you can do is you can heat it up. So if I had this thing and I heated it up, eventually we'd probably expect that cork to pop out of it. And that's because as I heat this up, I give these particles more and more and more energy, and so they start breaking free and turning into a gas and bouncing off of the walls. What's interesting about that is I can actually increase the pressure in here to the point where the particles are bouncing off of the surface with enough pressure, force, to keep any new particles from coming out into the vapor state. And so we achieve what's called equilibrium, and it's actually a dynamic equilibrium where particles of liquid are changing to gas, but then particles of gas are changing to liquid. And so there's always some gas bouncing around, but the amount of gas is not changing, right? We've reached what's called dynamic equilibrium there. Now, gas pressure is interesting because if there's so much pressure pushing down on the surface of the liquid that no more liquid can vaporize, then it's not going to boil. And so that means pressure can affect state or phase. Pressure can affect phase change. And this is actually why there's high altitude directions on things when you're cooking them. If you go high up into the mountains, this is my mountain, the atmosphere is got a lot of pressure down here, but less pressure up here. So if you're up here, water doesn't boil at 100 degrees Celsius. Down here it does. Up here it might boil at 95 degrees Celsius, which means it's not as hot. And that's because it's easier for water to boil up here because it's easier for the particles in the liquid to escape out the top since there's less air pressure pushing down on them. So high altitude directions sometimes alter cooking times, amounts of water you got to use. And it's because the air pressure actually affects how quickly it cooks. Now, what I want to do is look at how pressure affects phase change. And so this is a phase diagram, and down here is temperature. As we move to the right, this is hotter, this is colder. And over on the left side is pressure. Up here it's high pressure, down here it's low pressure. Okay, so pressure increases over here. This right here is triple point. Okay, so we know that if water is at 0 degrees Celsius, then it is going to be a liquid or a solid. And if I add energy to it, it could change to a liquid. If I take energy out, it could change to a solid. But it turns out there is a point where we can have all three states of matter at the same time. But then we have to just define not only a temperature, but also a pressure. So this triple point depends on temperature and pressure, and it only exists at one temperature and pressure for a given substance. These boundaries here, these phase boundaries, these are where phase changes can occur. So you can see if I have a solid and I add some heat to it, it will change to a liquid. Or if I have a liquid and I remove from heat from it, I can change it to a solid, right? We've got freezing and melting. But also consider over here, I have a liquid at right here at this temperature. If I put a little bit more pressure on it, or sorry, I have a liquid and I take a little bit pressure off of it, it's going to change to a gas. But if I have a gas and I put it under more pressure, it's going to change to a liquid. So I can get a phase change from changing the pressure as well as from changing the temperature. That happens over here. It's a lot more subtle with this one because this vertical change is almost following that pressure diagram, that pressure liquid boundary. Over here, of course, I can get it to change between a gas and a solid by increasing or decreasing the pressure.